Sounds good. Okay, perfect.
I'm very sorry for I'm very sorry for taking all the time, Lisa.
No, please, it's all good. Okay, so let's share the screen. Good. Okay, is there any question from the audience until then? Okay, so let's continue. What we've done so far is register the PAM50 template to the MT data. And we've also warped the template. So now we have access to the white matter atlas. And then we can do some what we call atlas-based analysis. So we're going to extract the MTR values within a particular funiculi of the white matter. So, a bit of theory. Prerequisite for any atlas-based analysis is to have an atlas. So in SCT, a digitalized version of the Gray's Anatomy spinal cord white matter atlas was merged with the PAM50 template. And for more information, you can look at the article from Levy et al. In 2015. In brief, the atlas is composed of 30 white matter tracts and 6 gray matter regions and the surrounding CSF. The reason for including the CSF is to be able to account for partial volume effect during the metric estimation, as we're going to see in the following slides. Let's imagine that the metric value you would like to quantify is 50 in the white matter and 0 in the CSF. Okay. Because of the coarse resolution of MRI, the apparent value within the voxel will be 25, okay, because it's a mixture between the white matter compartment and the CSF compartment. And this phenomenon is called partial volume effect. And so, as we will see, there are ways to minimize this effect or even to overcome it. So, because of its simplicity, the traditional method to quantify metrics is to use a binary mask, right? So voxels labeled as 1 are in the mask, are selected, and values within those voxels are averaged to produce, for example, an average FA inside the mask. But as we previously mentioned, this method suffers from partial volume effect, and the resulting metric would be biased by the surrounding tissue. So instead of using the binary masks, we could weight the mask, which effectively weights the contribution of the voxels at the interface. So, for example, we would have 0.1 at the boundary, and in the tissue of interest, we would have 0.9, right? That would be a weighting of the mask. So this weighted average method mitigates partial volume effect, but it does not solve it. And alternatively, there are methods using Gaussian mixture modeling that can be used to estimate the true value within the region of interest. So here we benefit from the fact that the metric is measured within thousands of voxels, where the partial volume for each compartment, which is the white matter, the gray matter, the CSF, is known. And then we can use maximum likelihood estimation to estimate the metric value within each of the compartments of interest. That is a good and reliable approach, but it's not robust to noise within very small tracts. Okay. Lastly, there is a method called maximum a posteriori, which is more robust to noise, and it uses a prior based on the average metrics within large compartments, with priors within the CSF, the white matter, and the gray matter. So it's usually the method that we recommend if you want to extract metrics within the probabilistic masks while being robust to noise. Okay. And to demonstrate the sensitivity of each method to the amount of noise and to the size of the tract, what we call the fractional volume, which is shown here, fractional volume of which is the percent of voxels in the white matter. We performed some simulations based on synthetic MRI phantom. So we have some like data, and then we have some tracts that we want to compute the metrics on. And what this graphic shows is that even if we look at very small tracts, for example, the rubrospinal tract, the error of estimation of the metric is usually less than 2%. Okay, when we use the maximum a posteriori method, whereas the weighted average method, as you see, can produce a high level of error. Okay, so that's why we do recommend that you use the maximum a posteriori or the maximum likelihood method. Okay. So let's do this. What we're gonna do is use the function extract metric, SCT extract metric, to compute values within each particular tract. So as you remember, the function SCT warp template will generate a folder locally called label. Inside label, we saw that actually we can look at it together. So I'm going to open the folder, single subject, data, empty. So we have a folder called label, and we have inside label, we have something called template, where we have all the prime 50 registered to the empty data. We also have a folder called atlas, and that's where the white matter atlas is. Okay, so we have our 36 plus 1 tract. This 36 corresponds to the CSF. And in addition to those nifty files, there is also a file called info label. This info label is the one that you're seeing here. Okay. And there are some, it basically describes the different, what those different files are. Okay. So the files 0 to 36 corresponds to the atlas, okay, all the white matter tracts, gray matter, and the CSF. And after that, you have something called combined labels. Okay, so we can, if I open it, you can see it here. And those combined labels are what defines the spinal cord, the white matter, the gray matter, the dorsal column, the lateral funiculi, and so on. Okay, so if you want to quantify, you know, white matter MTR, then you would select the label 51 because it corresponds to the white matter, which corresponds to the label 0 to 29. And 0 to 29 are these ones, 0 to 29. So these are all the white matter labels. And you can create other combinations if you like. You can create a line 56 with your tract of interest that would correspond to, you know, a combination of different tracts. That's something you can do if you want. Okay. So a bit more information about this info label file. It's generated, it's basically copied from the SCT installation folder. And as I mentioned, if you would like to add custom tracts to your analysis, then you can edit this file. And so in the example below, It was a request from John Brooks in the UK. He wanted to quantify data inside the left and the right hemichord. So we basically created these additional lines that were copied in the info labels.
Could the same thing be done for only ventral and only dorsal?
Absolutely. Absolutely.
Cool.
So if you want more context about the post, this is the post from John Brooks and all the explanations. So I'm adding this into the chat.
Very interesting. Thank you.
Okay, coming back to the slides. Okay, we are ready now to extract metrics, MTR. So we want to quantify MTR. The -F is pointing to the atlas that we want to use. Okay, by default, it's going to point to this atlas, so we actually don't need to write it. Right? If I'm typing SCT extract metric, the -F, the default is, oops, default is this one. Oh, is that right? Should be the local one. Okay, it's here. Default is label atlas. Okay, good. So let's do this. SCT extract metric, MTR, method. Now this is where we define the method. Remember when I was showing you the partial volume effects issue, we can use the maximum likelihood, maximum a posteriori, which we recommend, weighted average, bin. There are also other methods. You can compute the median across the different voxels, or you can also get the maximum one if you want. So in this case, we're going to use the maximum a posteriori. -L corresponds to the label that we want to use. So in this case, we want to do it in the white matter. So white matter from the info label is label 51. Okay, so that's why we are using 51. And the output will be a CSV file, which we'll call MTR in white matter. And that's the output. It's a table which shows the different slices, the label that we used, the size, the number of voxels that were used in order to compute the metric, and that's the result of the metric. So my MTR values is about 57, 41, 52. So this one seems to be a bit outlier because it's at the edge, but you see that the MTR values are relatively stable, around 52, right, across all the slices. Okay, does that make sense? If you want to list all the available labels, you can also type this, SCT extract metric list labels. You can do this. Now it shows you all the available labels and the combined labels. So again, which shows white matter. You can choose to quantify in the entire spinal cord if you want, or only the gray matter, and so on. Okay.
Can this analysis be also carried out using levels, like segmental levels?
Absolutely.
Slices?
Actually, that's what we're going to see right now. Is that the case? Yes. So you can. So as I said, you can specify other labels. So in this case, we're going to choose label 4 and 5, which correspond to the left and the right lateral corticospinal tract. Okay. So SCT extract metric minus I MTR. F, we don't need to specify it. We're taking the default. Methods, we're also taking the default. Label 4 and 5. Then we can specify the slices. We want to aggregate the metrics to slices 5 to 15. And the output will be MTR in CST. So that's my result. I have two rows. The first row corresponds to the white matter in the left lateral CST and the second one in the right lateral CST. Again, these are the size of the ROIs that were used, and that's the weighted average. Okay. And as Luis mentioned, we can also do the same thing specifying the vertebral level. Right. So for example, SCT extract metric minus I MTR minus L53 and vert to 4. So now we're going to compute that between vertebral level 2, 3, and 4. Minus, I don't need to specify vert file because it's the default. MTR in DC. So that's the dorsal column. That's my result. The slices 7 to 16 were used to compute at vertebral level 2 to 4. That's the dorsal column. That's the number of voxels that were used, and that's the value. Okay.
How would you get results at each individual level? Instead of aggregating them?
Right, if you want to this at each individual level, you would add the per level 1. Now I have the results for level 4, 3, and 2. The values here. Okay. All right, let's move to diffusion weighted MRI, unless there are questions so far. Okay. So first thing we want to do is pre-process the diffusion weighted MRI data. So we're going to go to the DMRI folder, and we're going to compute the mean diffusion weighted scan from the diffusion weighted data. So we're going to do an SCT math minus I DMRI, which is our DMRI scans, mean T minus O DMRI mean. Okay. Now if I look at this scan, the scan is actually an average of all the diffusion weighted images across time. And we're going to use that to segment the spinal cord. But the note here is that we're only gonna use the segmentation in order to create a mask around the cord. And you'll see why we do that. Yes, Pedro?
So apparently it's a better idea to use all the diffusion weighted images instead of only the B0. Why is that? Is it better
the B0,
contrast?
right? Yeah. So let's look at it. So that's the oops. Where's the B0? All right. So that's the B0 scan, right?
Mm-hmm.
So as you can see, so the CSF is here. So it's a T2 weighted EPI. lack of CSF
Yeah.
here because of pulsation effect.
Yeah.
Next slide, there is no more CSF. So, and here we even not sure where the spinal cord is. So the B0 is usually ugly, and you don't want to use that for segmentation.
Oh, okay.
Right? Because if you start to go from the diffusion weighted scan, they are noisy, but if you average them together, they show like a decent contrast.
Yeah, thank you.
And you will average in even if you have multi-shell data. So if you have different B values.
Right. Yeah. No, it's a good question. So in fact, what we're doing here is we are averaging everything together, including the B0. Right. You might not want to do that, and I can show you another command, which is called. Yeah.
Would it be more advisable to use up to a certain Q value and not all the shells, because you're gonna at some point you're not gonna have signal, or it's not gonna be it could be more detrimental than.
Yeah. So yeah, so it's a good question. So it depends on the B value, but also the orientation, right? So in any case, if you're averaging noise, yeah, you might want to avoid doing that. So to answer the question, yes, it is possible with another function called SCT DMRI separate B0 and DWI to separate the B0 and the DWI. And you can do that by specifying what would be the minimum B value considered as a DWI scan. Right? So if you have B values that are very low, for example, 50, you can consider them as B0 files if you use this flag here. So in this case, I'm gonna input my DMRI scan. We need to specify the BVEC as well. And I want to average my B0 and my DWI data together, but separately, right? So -A1. Okay. So it identified the B0, it identified the DWI, and then it will average all the DWI together. And it will be called DMRI DWI mean. Okay. So let's look at this. And we can compare this one to the one that we created above, the DMRI mean, which did include the B0 files, right? So I'm toggling between the DWI mean and the one that includes the B0. Right? So you can see that this one is a bit more ugly than this one. So in fact, maybe Sandrine, you can add a note in the course that in the course material slide 104, we might want to replace the SCT math with the compute, like DMRI separate B0 and DWI of this function here. Okay, so now we're gonna segment the spinal cord using the, let's use this one. So I'm deriving a little bit from the course material. In this case, I'm going to use the contrast DWI for the function deep seg. Okay. And I'm going to specify a QC report as usual. Let's look at the QC report. It's beautiful. Now we go back to the slides. We want to create a mask as we did for the MTR scans. SCT create mask using the output. So it's, oops, so you can see what's in there. That's the segmentation we just created. Okay, so I'm deriving a little bit from the course material there. CT create mask. I would be DMRI, DWI mean seg. Oh, sorry. As input image, we want to create the mask on. And the method will be using the center line, which is this one. That's the segmentation. And the size of my mask will be 35 millimeter. Okay, let's look at this. Okay, we're happy with that. So we're going to use this mask to do motion correction of the diffusion weighted MRI time series. So the diffusion motion correction in SCT uses a couple of features. It's using a mask in order to only focus on the spinal cord for the motion correction. It detects some outliers in case there is like an abnormal motion. And it's also using a regularized slice by slice translation, which is called the slice reg algorithm. So in order to run the function, you need to input SCT, DMRI, MOCO. The input will be your DMRI time series. We're going to use the mask that we created before. You need to specify what the BVEC file is, because it needs to know where are the B0s and where are the diffusion weighted scans. And we're going to specify the QC report as well. That's a new feature from SCT 5.4 that we now have a QC for the motion correction that requires segmentation as the input. Why this is running, I'm going to answer Pedro's question. Yes.
So the motion correction is based on rigid transformation.
So
or are you using a 12 parameter affine transformation to also account for eddy currents?
So the motion correction is non-rigid, but if you look at an individual slice, it is 2D translation. So it's basically TX and TY, but the TX and TY is different across the different slices. And the parameters.
I'm sorry.
Yeah.
Yeah, no, it's just I have my mindset to no, it's I have a mindset on brain imaging. So maybe the question it's it's just, but my question is, do you have the eddy current distortions also in this type of images you may want to correct?
Yeah, so we've worked on that in the past, and so I won't go too much into details, but I'm happy to elaborate on that in the forum if you ask the question. So long story short is that eddy currents are usually a problem when you're looking at pixels far away from the isocenter of the scanner. Because so there's like those sharing and scaling parameters, and those scaling and sharing parameters are as a function of X and Y. So since usually the diffusion weighted scans of the spinal cord are centered in the spinal cord, and we're only interested in the spinal cord, the sharing and scaling parameters are usually fairly like minor.
Okay.
And the other thing is that trying to estimate those eddy currents based on like blip up, blip down scans, if there is some corruption in the data, could actually create more harm than good. Okay.
There's also one question in the chat.
how it extract the lateral column regions. Oh no, I think we covered that. Is BVEC updated after registration? Ah, great question. The answer is no. Why don't we need to update the BVEC? Because we don't do any rotation, right? It's only translation. So there is no need to update the BVEC after the registration. It's a great question, yeah. So the next,
So,
yeah. So now let's, yeah, please, Pedro.
No, right now you don't have like you don't have implemented this in a way you can do population-based analysis of diffusion. So because in that case you would have to normalize the diffusion images, and then you would have to deal with the registration with the reorientation of the gradients. So this is all in native space.
So it depends what kind of analysis you want to do. So I usually, for the spinal cord, I usually discourage people to do tractography for a couple of reasons that I won't go into now. If you want to compute metrics such as DTI, FA,
yeah, that's not a problem.
There's no need to
there's
reorder.
no need.
Yeah.
Yeah, actually, you would normalize them after calculating them in the individual space.
Correct.
Okay.
Correct.
Okay.
Yeah.
Thank you.
So let's look at the QC reports. And you can see that there is a small GIF animation showing the before and after motion correction for all the different diffusion volumes. Going back to the slides. Once you registered your diffusion weighted time series, we can finally segment the chords in a more robust way now that the data are motion corrected. So we're going to run SCT DeepSeg again. But this time, we're going to input the MoCo DWI mean data as the input. The contrast is the same, diffusion weighted image. And we're going to do our QC report. It's fairly fast because we don't have a lot of slices. And it looks fine. Next is we want to register the template to our DWI scan. Again, accounting for T2 star T2 star gray matter segmentation. So I'm going to take this big line and copy it. And I'm not going to do the same error as I did before, but I should use the line from the web browser, so there is no error in pasting. This one, line 261. Here we go. And then we're gonna warp the template. And while this is warping, we're gonna look at the QC report. Okay. So refresh, register multimodal. So what you're seeing here is the T1 weighted PAM50 template registered on the DWI scan, right? So why did you decide to take the T1 weighted PAM50? It's because the contrast is closer to the contrast of the DWI scan, right? It's the CSF dark and chord bright. So warp template is finished, so we can look at the QC, and again it looks fine. Once you once you've done the registration to the templates and motion correction and so on, you can compute DTI Matrix. So you can do that with the function SCT DMRI compute DTI. The input will be the motion corrected DMRI scan. You need to specify the B-val, and you need to specify the BVEC. Here we go, and let's look at the output. There are new files that were created here, the DTI AD, which corresponds to the axial diffusivity, fractional anisotropy, mean diffusivity, radial diffusivity. Okay. And now we can take those and extract metric, like as we did for the MTR, but now we're doing it for the DTI matrix. So SCT extract metric minus I would be DTI FA, for example. Minus F is by default, we don't need to specify it. Method map, it's by default, so I'm going to specify that I want to compute this between vertebral level C2 and C5. And I want this per level. And my output will be FA in white matter. And I forgot the L51 because this corresponds to the white matter. Okay. We can open the results. And it shows this is our results. That's the average fractional anisotropy in the white matter at level 5, 4, 3, and 2. So you see that this is pretty like the value is relatively stable across the different levels, which is what we would expect from this metric. Any question? Maybe there is a question in the chat. How good will registrations to the template be without a proper T2 star? So yeah, as I said before, they will be very good. So don't worry about it. Don't bother with the T2 star. I was just showing it in the course for the purpose of showing that this is a possibility. But yeah, don't bother with that. That's my message. Yeah. Pedro?
Sorry. So is it possible also to save the eigenvalues instead of the measures themselves?
Yeah, let's see. Is that I vaguely remember someone was asking that a few years ago. Did we implement it? Yeah, we did implement it. Awesome.
Okay. And the eigenvectors too. Excellent. Good.
Exactly. Yeah.
Okay. Thank you.
Other questions? If not, we can move on to the functional MRI section. So
just
in this,
one last quick question.
Oh, yeah, sure.
Yeah. So I'm assuming you can also do extract these values based on the tracks, right? The different cortical spinal, spinal.
Absolutely.
Okay.
Yeah. Yeah, like if you do an SCT extract, so it's the same function as what we used for the NTR, right? List tracks. What is that? List labels. So we can rerun the same command, SCT extract metric, but instead of L51, we can take the first 4 labels here. For example, you can do 0 to 3, right? Or like 0 to 10. And I'm going to call it FA in tracts. And you can open this. That's a bit overwhelming because then for you have vertebral, 2 to 5 for the fasciculus gracilis left, 2 to 5 for the right fasciculus gracilis, and so on and so forth, right? Yeah, functional MRI, right? We're getting there. Good. So, yeah, I mean, this section is really about the pre-processing, right? So we just want to cover the to scratch the first layer of FMRI analysis. We're gonna go to the FMRI folder. And the first thing we want to do is similar to what we did for the diffusion weighted scans. We want to first average all the time series together. And then we're going to bring the segmentation from the T2 scan inside the space of the FMRI scans. From that T2 segmentation, we're going to create a mask that is centered along this segmentation. And then we're going to do a motion correction using that mask. Okay. So the reason we do that is because it's the most reliable way to get a first segmentation on a non-motion corrected fMRI time series, which could be pretty ugly, right? And if the subject did not move too much, then the T2 should be fairly close to the fMRI. Now I realize that what I'm saying could be wrong if there is a lot of susceptibility distortions, for example. So again, this is just an example, and you should not take this and apply it verbatim to your analysis. You should always adapt based on the data you have. So SCT math FMRI mean T. So we're going to average across the time dimension. And we're going to call this FMRI mean. Okay. Let's look at this. So that's the average FMRI scan. You see, it's not that ugly, but it's ugly enough that the segmentation will not be very well executed. Could still work though. So I could bypass what I wrote here and do a first segmentation path and then use that to create a mask. It's something that we could do. Again, there are different ways we can go to Rome, but I basically went with those lines so just to show you what are the alternative approaches. Okay. So we're gonna bring the T2 segmentation in the space of the fMRI using register multimodal, but we're not gonna do any proper registration. We are just doing a regridding, right? We're taking the T2 segmentation, which is in the space of the T2, and we are just resampling it in the space of the mean fMRI that we just created. And that's where the identity one comes in, right? The identity one means I don't want to do any registration. I just want to do a regridding, okay, like a resampling, if you will. So let's look at the result of that. So what you see here it's not too bad, right? That's what you see here is the in white, it's the segmentation of the T2 weighted image that is resampled in the space of the FMRI EPL. Right? So there is no registration here. It's simply a resampling. So we can use that reliably to create a mask around the spinal cord that we're going to use to do the motion correction. Okay. Ken, yeah?
Yeah, that registration looks really good with just resampling. Was the field of view centered exactly the same for the T2 and for the functional there, or? No,
absolutely not. This is independent on the, because it's using the Q form of the nifty header, right?
That's like or the scanner coordinates or something.
That's exactly it. And okay. I'm going to actually demonstrate that if we open Facilize FMRI mean. I'm opening this image, okay, which is in a particular which has a particular pixel dimensions, right? 113. And on this, we're gonna overlay. That's the nice thing with Facilize compared to FSL View. For those who are like old enough to remember, FSL View was the previous version of FSL Viewer. So I'm gonna select the T2 image, which is this one, right? There is no registration. I'm just opening it. And so what you can see is if I'm toggling the T2 on the fMRI, they are kind of registered, but not so well, right? And there was no registration here. I'm just taking these two images were acquired during the same session. The participants, did not move too much. Was probably nothing, and yeah, that's reasonably good. Again, there is minimum distortions and so on, but yeah. So now we want to create a mask. And then from this mask, we're gonna do a motion correction. So how many of you here are mostly into fMRI? So I know Rob, but that doesn't right. Ken, right? Pedro as well. Okay. Okay. More than what I thought.
Julian, interestingly, this is precisely what Rob programmed to do 10 years ago with fMRI. So have generate like a Gaussian mask around the spinal cord by just enlarging the mask and then doing motion correction.
Yeah, it's really nice to see this, Julian. This is really cool. I wasn't actually aware that this was available in the Spinal Cord Toolbox, actually.
Yeah, no, this is very useful. Very, very useful.
So is there any, I might have missed the previous explanation when you give, is there any optimal radius for the cylinder?
Yeah, that's a great question. The boring answer, it depends on the data. Why is that? Because if you have participants that are in the scanner and move like this,
yeah,
then obviously a mask of 35 millimeter will be too small, right? That's my answer.
I mean, you can always align them manually, I mean, that's a first approximation, and then you can select the smallest cylinder. I think, you know, small the better.
Yeah, the
Because
smaller
you have
better,
less-
but the problem is that if you have like a time series of 500 volumes,
Oh,
and
you're
there
right,
is
yeah.
like an excessive motion at volume number 385, you know,
Yeah,
you don't want to.
you're right. You're
Yeah.
right. Yeah, this is not the brain that you can trust in an automatic fashion. Like, you know, you
Mm.
can, but it's not the same thing.
I mean,
There's a
what
lot
you
of-
could do is
There's a lot of things out there.
Yeah, so you could almost step registration. The first step, you have like a very big mask
Mhm.
that will take care of the coarse motions, and then step number
Hierarchical,
2,
yeah.
you can take like a smaller mask.
So you can do in a hierarchical way and reduce the mask and actually maybe, you know, you can come up with a method to automatically find, you know, something like
Yeah.
zooming down.
Ken, I think you wanted to say something?
Yeah, I was just wondering, is this also limited to translations only with,
It is.
Okay.
Yeah,
but not along the z-axis, just in plane?
just in plane, absolutely. So if you go to FMRI MoCo, so these are the different parameters. And if you go with the param flag, you can adjust some of the advanced parameters. So, I mentioned that this is 2D translation, but they are regularized along the superinfrared direction. Right? And this regularization is currently using a polynomial function of degree 2. You can increase it if you want. There are the other parameters that you might want to play with, but in general, those will not have like a big impact on the FMRI time series. Yeah. If you're dealing with extremely noisy data, you might want to group successive volumes together. For example, you can group volume 1, 2, 3, and then register this group into volume 3, 4, 5, and then 6, 7, 8, 9, 10, 11, and so on. Okay. Right, so now that we've done this, I'm gonna run this, and then we can look at the results of the right. So I think, Lisa, that's exactly the error you had, right? And the reason I'm getting this error is because I copy-pasted from the PDF. And if I copy this from the file on the browser instead.
Julian, it's actually the version problem. I posted on the forum and Josh Newton responded back.
Oh.
And now it works. The -O warp inf that was introduced in version 5.4. So once I remove that, it now works. And it generates a different output file name. So I just had to rename that.
Okay, sorry about that. Okay.
No
well, thanks
worries.
for the
Thank you.
Thanks for the feedback. So, but in this case specifically, the error was due to me copy pasting from the PDF. So yeah, let's look at the QC reports for the FMRI MoCo. So I realize if you have like, 2000 volumes, that's probably like a boring Saturday night to spend. But yeah. Okay, this is done. QC report. And what you're seeing here is I'm toggling between the average motion corrected FMRI and the registered T2 weighted scan, T2 star weighted PAM50 template. Okay. So, there are some locations where there's strong susceptibility artifacts. So obviously you want to be very careful making sure that the registration is reasonable. Yes, Ranga.
Yes, Julian. I did the motion correction and I'm just looking at the data in a different viewer on my computer. And actually after volume 42, I see induced motion in the motion corrected data, which I don't see in the raw data.
It's highly possible.
Do you know why that might be the case? The card literally moves in the anterior posterior direction after correction.
You said volume 40.
From 42 to 43.
Actually, a nice way to look at it is opening two. Right, it's opening another one. So that's the original, and that's the motion corrected. You want to make sure you use the same value here. Okay. Good. So, oh, that's bad. Yeah. Yep, I agree. So, yeah, so yeah, that's pretty bad. That's pretty bad. So if you, what's interesting is that if you look at the sagittal view here, you can see that there is some sort of bending, right? So that's typical of the polynomial order 2 of the slice reg method. You know, what's difficult is that if we overlay the mask, it will tell you a bit more about what the algorithm is trying to deal with. So we are trying to estimate a deformation field. We're trying to estimate a deformation field on this amount of voxels, right? So that was a question before, you know, how big should the mask be? Well, in that case, maybe the mask is just too small. Right? So if we, so I would do two things here. Either I would, so I would try with a bigger mask, right? And I would also try grouping the scans, you know, using the -G. Oops. -G flag that we talked about before. Right? By default, it's 1, but you know it could increase the SNR. But I would start with playing with the mask, because I think that's really the critical aspect here. There's another parameter that plays a role in the registration. It's the metric used. You know, by default, it's the mean square. If the overall image intensity change, then that will affect the mean square metric, because the mean square assumes that the intensity of the source and destination are the same, whereas the cross correlation will normalize it. Right? So you might want to try the cross correlation, which is slower, but might be more robust.
Okay.
Yeah.
Okay, I'll try it later, and I can.
Yeah. That's actually nice. Sandrine, maybe could you add a note to this, like that we need to check that we should actually discuss this problem of registration and then discuss what are the mitigation strategies for this. So we talked about increasing the mask, changing the metric as well.
So you have cross correlation and sum of squares, those two.
Mutual information,
mutual
mean squares,
information?
and cross correlation.
Oh,
that's
okay.
right. That's right. Yeah.
Oh, mutual information. You also have. Okay.
Yeah.
Oh,
yeah.
I'm seeing it there. No, I didn't see it before. It's the MI, isn't it?
That's correct. Yeah.
That's the one. Okay.
Yeah. Yeah, Rob.
Sorry, I just wanted to say, Julian, I believe what you said is completely correct. I spent a lot of time fiddling with motion correction and the size of masks. Initially, I thought that making the mask smaller would be the best way to go, and that was wrong. When I made the mask a little bit bigger, it actually didn't make a huge difference because the area around the cord was black because of the bones. You're basically adding zeros, which doesn't change anything.
Yeah.
And then I made it
Yeah.
a little bit bigger still. And then you get into the contrast between the bones and the other muscle and fats around. And that actually provides, actual information to guide the registration algorithm. So as you just said, I found the best approach was to find that happy medium where it's big enough to actually extend past the bone and include some of the boundary between bone and fat and muscle, but then not much further than that, because then the distortions and whatnot, definitely don't help at all. So it's definitely a, fine balance.
Yeah, that depends on the data as well. Yeah, you could also play with smoothing. That's another thing that could help. This parameter here. Yeah, you can spend an entire PhD about what's the optimal parameter for spinal cord FMRI motion correction.
Exactly.
Okay. So, oh yeah, Ken.
Yeah, I just had a question back with the registration of the command you ran. So you used the intensity of the image for this registration, right?
Correct.
For the
correct. Yeah.
And the reasoning for that is because the automated segmentation doesn't work, and you want to make this automated. I guess my pipeline I manually try to identify the cord as best as possible.
Okay.
Just your thought and the reasoning for that.
Right. So for this course, I didn't want to enter into like manual correction and things, but I would strongly recommend for fMRI studies to indeed rely on the spinal cord segmentation for the registration. Absolutely. Yeah. In fact, that's something I should mention in the course. Could you, Sandrine, please add also a note on that? Yeah, thank you. Yes, Pedro?
Yeah, and the final thing that I have regarding the fMRI is, do we need to smooth the images for first level analysis? Like we do with the brain? Like, and if we have to, what type of smoothing kernel? I mean, is it an anisotropic kernel? What type of kernel do we need?
Right. So again, boring answer is it depends on the data, and it depends on the hypothesis. For example, if you're looking into clearly distinguishing the ventral from the dorsal horn of the spinal cord in your GLM results, then you might want to avoid strong and big kernel in the in-plane direction, right? If you anticipate that you will have like a large pool of neurons that will activate along the superior and inferior directions, then smoothing will help. It will help. But by smoothing, that's something we'll see in one of the slides later, is that smoothing will also depend on your current slice thickness. If you have like very thick slices, then smoothing might be problematic because it might also include some interpolation error, especially if the cord is curved. If you have like one slice that is like this, or like, how should I say? If the cord is like that, and your slices are not perfectly orthogonal to the cord, then if you smooth along Z, you will introduce some partial volume. So smoothing will actually blur out your activation. So there's a lot of tricks, like challenges and tricky parts.
Yeah, I'm actually, I would not smooth because I don't see, it's very small in the in-plane and then I don't think it's a good idea to smooth across the slices because they are too thick. That's what I mean when I think of the problem. That's what I believe. But I'm thinking that usually in the brain you have to smooth in order to make the noise more amenable for for the GLM. That's my concern.
Yeah. So I mean, I would say there are different schools, right? So when I was like John Polimeni, who is like a colleague of Rob Barry at MGH, likes the effective native spatial resolution and looking at like the different layers in the cortex by smoothing would effectively reduce that nice resolution. So one school of thought is that if you are to smooth later on, why not acquiring the data with a coarser voxel and not smooth? Because acquiring with coarser voxels helps you to reduce the matrix size, reduces the susceptibility distortions, rather than acquiring at super high resolution with noise and then smoothing later on. Right? So I'm not convinced that smoothing is a necessity in fMRI in general, but I know this is a controversial topic. Ken?
Yeah, just to comment on that, I think it's a great discussion. And like all these steps, we don't know maybe the best answer. And of course, like you say, it depends on your analysis. And for task-based fMRI, I have a few posters. I don't have a paper out, but that there can be maybe some benefits from smoothing, but something where you're doing an ROI-based resting state analysis, taking that a mean signal in that ROI is a type of smoothing. So just some thoughts.
Yeah, thank you. All right, so last consideration of the fMRI is that you're obviously interested in the intrinsic spinal levels and not the vertebral levels, because that's where you base your hypothesis on when you want to interpret your results of the level of the activated neurons. So we warped work from David Cadot, who is a neurosurgeon. So he did this study in 2015 based on 20 adults, and it was basically a mapping of the spinal levels versus the vertebral levels. So he generated a probabilistic mapping of the distance of those spinal levels with respect to the pontomedullary junction. And so those levels, those probabilistic spinal levels are available in SCT. And you can warp those spinals level using warp template, SCT warp template. So if we type SCT warp template, we look at the help. -A is the white matter atlas that we used before with SCT extract matrix. And there is -S, which we haven't used so far, but it corresponds to the spinal levels. Again, these are probabilistic based, right? So there is no actual segmentation of the spinal levels in your particular participant. So it could be improved, but I would say this is a start. Could be better than nothing in some cases. So D would be the destination. So we're going to warp the template on the mean motion corrected fMRI scan. We're going to use the warp template to fMRI warping field. And we want to output the spinal levels. And we don't care about the white matter atlas. Do I have a right? I actually have a command here that I can use to open facialize with the right view. So what you see here it's the overlay. So the color coding corresponds to the spinal levels, right? So it's a probabilistic one, which is why it doesn't have the same intensity. Right? So we have like spinal C2 would be the brightest red, sorry. And then it goes to the next spinal levels, which would be in blue, and then in green, and then in yellow, and so on. Okay. Sorry, it was this C3, not C2. Any question on that part?
How robust will something like this be on a pediatric population?
Yeah, right. For pediatric population, I would not trust that spinal labeling. It has not really been validated on a pediatric population. No. So that's an open question. And thank you, Rob, for your thoughts that I can see on the chat here. It's 4:45. I'm not sure, Rob, what was so there is probably another, is there another break that was done or not? Because
yeah, according to the calendar, Julian, we're wrapping up in the next little while, and then it's informal discussions from 5 to 6. So basically, if you need to, wrap things up in the next 20, 30 minutes, that's fine. Or if you want to go for another hour, that's fine too.
Okay, so I think, there's like a total of like, we haven't done, well, actually 149. Okay, not too bad. Okay, so I'm going to take the last 15 minutes to show you 2 things. One is the quality control report, and the other one is the Facelize integration. The quality control, I'm going to show this to you when we talk about the batch processing, because I really want to show you the batch processing. I think it's a very important aspect of the talk. So let me quickly show you the Facelize integration. So if you open Facelize, there is a possibility to load an SCT plugin, which is called SCT plugin, and you can access it from the Spinal Cord Toolbox installation under the contrib folder. And if you open that, there is a new window that pops up in Facelize, which is this integrated Spinal Cord Toolbox GUI. So with that, you can actually run Spinal Cord Toolbox within Facelize, so without any without having to interact with the terminal commands. So for example, if I'm opening the empty scan, and then I can run propseg. So you have to click on input file. It will select the file that is selected on this window here. You select the contrast. So in this case, it's a T2 contrast. And then you can run. You can see the terminal output in this little window here. And the output is automatically displayed on the Facelize window. So yeah, we find it very cool, convenient for those who like the GUI. And there are many other commands that you can have access to as well. The deepseg SC, gray matter, vertebral labeling, register to templates, and so on. So that's about it. I talked briefly about the smoothing along the spinal cord. I'm not going to spend too much time on that, again, out of the for the interest of time. So I'm going to jump right away into the analysis pipeline with SCT. Okay, so we're going to spend our last 10 minutes on this. So the concept here is that I strongly recommend everyone to work with batch script so that your analysis can be run into like a section of commands, as Rob mentioned with MATLAB script. That's exactly the same concept. We can do it with MATLAB. We can do it with Shell, with other languages, with Python, and really the philosophy is to be able to have reproducible results. So if you work on some projects, you process like 150 subjects, and then write the article, and then 6 months later, reviewer number 2 is asking you to try a slightly different parameter. Instead of basically reopening all your images, your terminal, and then rerunning all the commands, what you could do is take your batch script, change one slight parameter, 30. You change this 35 to a 40. You save it, and then you rerun all your 150 subjects, right? So this modification should take you a few minutes, as opposed to a few hours, days, weeks of reprocessing a lot of subjects. Okay, so it's extremely powerful, extremely powerful. Using batch scripts require your data to be well organized, and so one of you mentioned about the BIDS folder. So BIDS is a standard for organizing data sets, which I encourage you to follow. And what we're going to do here is play with the data set called the multi-subject data set, which is organized according to BIDS. Okay, so we're going to go there. Yes, so we're going to go to multi-subject. And if you want to know what's in this what's in this folder, we can do find data, and it shows all the data that are in there. It's like subject 1 has the ANAT folder, and it has a T2 weighted scan. It has an empty on and empty off scan. And we have 3 subjects: subject number 1, subject 5, and subject 3. Okay. So to process these 3 subjects, we have a script which is called process data. Okay, so let's see what's in process data. Let's open it. It has a bunch of commands, which I'm going to describe later on while the script is running. Okay, so we don't lose too much time. So what I'm going to do is run this command here, and then I'm going to explain what it does. Okay. So what I did was running this command, SCT run batch. So what SCT run batch does is it takes a script as input, which is this one, okay, process data.sh. It takes as input a path to your data. In this case, it's the data that are right there. So I can actually open them so that you can see them. I'm opening them in the Finder. So it's multi-subject data, right? So that's the input that I gave to this command, okay? And path output is where I want the output to be located. In this case, I called it output, and it's this folder here. There's an additional parameter called jobs, and jobs is the number of CPU that you want to use for this command. Here I have 3 subjects, okay? So I want to use 3 of my CPU cores to distribute the processing across those three different CPU cores. Okay. If you have 200 subjects to process, and you have 16 core CPU, obviously you can't use jobs 200, right? You need to use the appropriate number of jobs depending on your CPU. Okay. Also, if you max out your CPU, you might not be able to use your laptop anymore. Like,
yeah. Quick question about that example. So imagine you have 16 cores, but you have, let's say, 50 participants to run. Would you choose 16 jobs and assign one core to each, or would it be better to assign multiple cores to each?
That's a great question, and it's a difficult one. It depends on a couple of things. It depends on what is inside your processing script. If it's like tasks that are very low CPU intensive, I would just use all my CPU cores -1, because I still want to have one CPU core for my OS, right? So always keep one for your OS. And if I have CPU and RAM intensive processes, then I would not be too greedy about it, right? Because if you max out your RAM, then you're stuck, and then you end up having a processing that is slower than what it would be if you had used a lower number of jobs. Right? So I invite you to yeah.
So for a rule of thumb, how much RAM will you assign to each job?
Oh, it's very difficult to tell, because it really depends on the process, on the data as well. If you have data with big matrix size, a lot of slices, that will take up the RAM very rapidly. So I have like 16 gig in my laptop. You can see that it's actually, is that right? No. This is not a proper estimation. Actually, my RAM will be shown here. That's my processors. So I can use this. So I still have some room, right? And in terms of CPU, I probably use like half of it, so I still have room here as well. But in general, yeah, I would look at the RAM consumption, and then adjust, like you can do a trial. You can start if you have like thousands of subjects to process. I would do a start with with a given number of CPU cores, and then monitor the RAM and see if you saturate or not. Yeah. Pedro, you had a question or comment?
No, I wanted to know if it's possible to run this batch in a Slurm environment.
Yes, the answer is yes.
Okay,
really
awesome.
powerful.
Because that's
what
I have.
Yeah, you can, and in fact, so please, if you can follow up with us on the forum, we can give you an additional script that will generate a Slurm command that will break this down across your different subjects. Yeah.
Thank you.
Okay, so running this will give you this output. So it gives you some information about the OS you're running, the CPUs, the RAM, and so on. Lists other arguments that you've used. Here it says script. So these are some information about the input script that you used, right? So in that case, I used the local script, which is called processdata.sh. Okay. But if you want, you can also input a script that is inside the Git repository. And if you do that, it will look for the commits of the script, and it will also look for the actual URL of the script on GitHub. And that provides a really nice way to be able to reproduce an analysis if you put your script on GitHub. Right? The same way with the data. I used local data, okay, but you can also download data from a GitHub repository, and then it will list here the actual commit number and the URL of your repository. So it makes your processing 100% reproducible, because within this output, within this log file, you have the data, you have the script, you have their version, and you also have the SCT version that you use to process your data. So again, I strongly recommend every one of you to adopt those practices for processing. Now let's look at the output. Okay, so we have an output folder that has data processed. So these are the data that are copied and currently processed. Okay, we have a log folder. The log folder has this thing, this output, which you're seeing on the terminal. Okay, if I open it, basically lists everything that that I presented you so far. And it also has a log file for each subject. Right? So if we look at subject number 1, it shows the different, like the output of the processing for this particular subject. Right? So, you know, it's a bit boring when you look at it, but in case you have an error, then you can look inside the log file to understand what would be the cause of the error. Okay. You also have the QC folder. That QC folder is the same as what we've done so far. So you have an index that you can open on your browser, and it shows, so we can actually order it by subject. Okay, so you have all the processing for subject 1, subject 3, subject 5. And you can see the result of DeepSeg on the T2, variable labeling, registration to templates, warping of the templates, segmentation on the MT scan, and the same for the other subjects. Okay. And finally, you have also a results folder that outputs what I asked to output in my script. Right? So I asked for the CSA value for every subject. So now each row corresponds to a subject, subject 3, subject 1, subject 5, vertebral level 2 to 3, okay? And that's the mean cross-sectional area for each of the subjects. Okay. And so again, this is fully automatic. So imagine you have like 5,000 subjects to process. You can basically have an output file like this across your 5,000 subjects. And the results of the MTR just came out as well. And it's basically we're asking for MTR in the dorsal column between level 2 and 5. And that's the result. Right? So you can see that the MTR value is very reproducible across the 3 different subjects. So we're going to take the last few minutes to show you what to do if something goes wrong. Right? You're looking at your QC. I'm going to go to the slides here. So these slides just explain what I just explained to you in the results folder. Now, checking your QC report, if you see that something is wrong in your segmentation, then you can report it. And that's what we're going to do now. Okay. We're going to search for all the DeepSeg segmentation. So I can type DeepSeg here. So I'm just listing the DeepSeg segmentation. And now with your arrow, you can navigate across all the different segmentation, okay, all the different process. And with the letter F, which is here, you can describe if you consider the QC to pass, to fail, or if there is an image, an artifact in the image. Okay. So if you press F, there's a new QC column here that gets filled. So I find that this segmentation is fine. So I'm putting an OK. This one, let's say I don't like it. So I'm putting a cross here. This one, let's say I don't like it because of this problem here. So I'm putting a cross. This one, let's say I like it, I like it, I like it, and so on. So you can do this process across all your subjects. And when you're done, you can click on download QC files. And this will download the YML file that will list all the subjects that require some manual corrections. Okay, so that's the YML file that I just created. How can we use that YML file? We're going to use it with another script, which is on my folder here, in multi-subjects. And the script is called manual correction. So you can customize the script to your needs, but right now I'm just going to call it, and I need to explain to you a little bit. This manual correction script requires FSLIs to be installed, and also to be able to run within the while we have activated the SCT environment. So I'm not going too much into details here, but you can just copy paste these commands. And then we're going to activate the SCT Conda environment so that we can use SCT's Python, because we don't want to reinstall Python. Okay, we can just use this one. And now we can use the manual correction script, right? So if you write Python manual correction -h, it will explain what are the possible options. Okay. And what we're going to do is run this manual correction. So Python manual correction. The config file will be this QC file that we just created. So it's located in my desktop. Path in is the processed data. Okay, so it's output data processed, and the path out is the actual data where you want to create the manual corrections. So it's a bit confusing because it looks like the original data is considered a path out. Now, why is that? Because imagine that you have a data set of 250 subjects on which you want to create manually corrected segmentations on, let's say, 5 of them. You want to save that. You want to save those precious manual corrections, right? Where's the best place to save that? Well, you can save that under the derivatives folder of the original BIDS dataset. And that's compliant to the BIDS standard, which suggests to put the derivatives of native datasets and to basically package it as is. Okay, so that's what we're gonna do here. I'm pressing enter. It's checking if SCT and FSLIs are installed. Then it's asking me for my name. Why does it want my name? Because I'm going to do some manual correction, and I want to know 6 months from now or 2 years from now that I was the one who did the manual correction, right? This will be encoded in the JSON file that is sitting next to the Nifty file, again, which is BIDS compliant. So this is my first image to correct. So let's say that I don't know, we're just gonna zoom in here. You click on edit, then you can add up. Let's say you want to add this. Then you save. You can overwrite. It's fine because it created it under the under your data derivatives. So it basically created a new file called seg-manual. Okay, so you can click on overwrite. Then you can quit that. And then it opens the next subject to correct. So again, let's say you do this. Edit mode. And this, and then save, overwrite, quit, and it's done. What did it do? If I go to my original data, which is here, it created a new folder called derivatives, right? And under these derivatives, down there is no labels folder with the corrected segmentations for subject 1 and subject 3, right? So that's the corrected segmentation, and that's the JSON file that has my name and the time, the date and time where I did this correction. Okay, and now you can take this entire data folder, zip it, package it, and share it with your friends, family, and so on. And that's basically, or you can also put it on GitHub, update the version, the release of your data set. And now you can version track exactly the data set you used to generate a particular results, set of results. Right? So if now I run this, the same SCT run batch again, I'm going to do this here. You see that for the path output, I used output correction instead of output. And the $100 question is, how does the script know that it should use the manual corrections as opposed to just redo the segmentation? It knows it because I ask the script to do this. In the process data, look into this. There's a bunch of, oops, the script starts here, okay. There's a function here which is called segment if does not exist. Okay, so this is a shell function, and it's defined here a bit more up. Segment if does not exist is basically this these lines of code. It first looks for the manual segmentation. Okay, so if it exists, if it finds a manual segmentation, it will use it, and it will just copy it locally, generate a QC report. If it does not exist, then it runs dipsag-sc and it runs the segmentation. Okay. I know it's a lot of information for the end of the day.
So if you're a bit conservative with your manual corrections in a first pass, could you reiterate this process and do it again, and it will find the next corrections? If you go back and correct again.
Right. So exactly, because if we use a manual correction, then we still generate a QC report, right? So if you want to double check your new QC report, you can do that. And if you're still unhappy with the manual correction, then you will select your manual correction as like a fail, and then you can consider it for the next stage of manual correction.
And then those corrections, the metadata will get appended to that JSON file?
Yes, it will be copied, it will be overwritten. Yeah. It will not be appended, but overwritten. Yeah. But that's something you can customize in the manual correction script.
Thanks.
So that's something fairly recent. So we are still working on the, on the procedure, and but we would love to have your feedback on that approach, to make it more streamlined and accessible for the crowd.
An idea that I have while you
Yeah.
were going through this was sometimes we like to have more than one set of eyes when something is manual. So if you have multiple users doing manual corrections, it would be good to be able to append that metadata, so we know when the
that's
lab
great.
has touched that file.
That's a great idea. Great idea. Yeah, it's fairly easy to do, in fact. But yeah, that's great feedback. Yeah, thank you. I think that is pretty much it. Maybe we can spend the last minutes talking about the new features, and then I'm gonna end, I think. So let me just go to this slide here. We have a new website. Probably all saw this, so that we are trying to integrate into the website the different tutorials. So the tutorials that we've done today are accessible in this page here. So all the tutorials for the segmentation, registration to the templates, and so on. That's amazing work from Joshua Newton. So if you have any feedback, please share it with us. We would love to know if this is useful and if there are like better ways to present it. If it's too overwhelming, if there is too much information, not enough information, and so on. New features. So SCT 5.2, we introduced a new function that I didn't talk about today, which is called SCT DeepSeg. And in brief, SCT DeepSeg purpose is to replace the current DeepSeg SC and DeepSeg GM function. So SCT DeepSeg is already accessible, and it has a bunch of options, and one of the options is to list the different tasks. So you can see what are the tasks that are currently available in DeepSeg. And you can see that a task has a collection of models, right? So we've been contacted by collaborators who, for example, wanted to segment the spinal cord in mice, or the gray matter in mice, or the tumor in T2 weighted scans. And so for each of these cases, we created a collection of models that you can all access. So for example, if you want to segment the gray matter, the gray and the white matter on ex vivo human T2 weighted scans, then there is a model for it, right? So down the line, we want to deprecate DeepSeg SC and DeepSeg GM and replace it with this DeepSeg function. Okay. So that's coming at some point. So don't be, so you're prepared if at some point you see that SCT DeepSeg SC will disappear. Okay.
Will SCT DeepSeg also be useful for identifying lesions in gray and white matter?
Yes, that's the plan. That's absolutely the plan. We currently have a project, actually including Ken, who is on this call, or maybe no more. But yeah, we have a project with folks in Zurich, Stanford, UCSF, to create a model for SCI, like spinal cord injury segmentations, and also another model for MS lesion segmentation.
Okay.
So yeah.
Well, keep us posted, because we're going to be acquiring data sets in MS patients at 7T. So I don't know how many data sets like that, but we'll have lots soon.
Okay, so you should definitely keep in touch for that thing. Oh yeah, so that's what I was just talking about the SCI and MS lesion segmentation. Another thing that we are working on is an improved vertebral labeling, because the one we currently have is not working, as much as we would like to. So we now have a different-based approach for the segmentation of the labeling of those discs. I think contribute, right? I think we can jump directly to the acknowledgements. I wanted to spend some time to acknowledge everyone in the who is working hard to make SCT a sustainable open source project. With Joshua, Nick, Alexandru, Charlie, Andrian, Sandrine, Jan, and all the alumni also who contributed to this software. Collaborators who have also contributed to some of the features. Thank you very much, Rob, for sponsoring this year's SCT course. It's greatly appreciated. And thank you everyone for your feedback and for using SCT.
Thanks, Julian. This was absolutely fantastic, and you must be tired. It's a whole day of talking, but I think it's worth it.
Thinking about the beer that I'm gonna have in an hour.
As a complete novice to spinal cord injury imaging, I think this was a great introduction. Thank you so much for your time today. It was great.
Thank you. So yeah, I guess we have some time now for the informal discussions, right? I guess it's informal, so we can go back to some aspect to some parts of the course that we'd like to clarify, or we can talk about anything, music,
Yeah,
art.
I'll turn off the recording now.